So we know that Newton's law of motion, F is equal to m into a. This law is modeled for a point mass. Let this is a mass of point mass having mass m. If force is exerted F, then acceleration will be of this point mass will be F by m. This is Newton's second law of motion. This is applicable for a point mass. But in real life, we encounter with real objects having finite size. So, to understand the motion of these finite objects, real objects, we have introduced the term called rigid body. And there is separate branch of physics to deal with the mechanics of rigid body, which is called continuum mechanics. Continuum means a continuous mass. Simple term, it is continuous mass. So continuum mechanics is a part where we study the motion of continuous mass rigid body. So Newton's law of motion are applicable only for point masses. And similarly, addition of vector, subtraction of vector, which we have discussed earlier, they are also, we have discussed as a point, they are passing through the same point. So they are acting on a single point, like force. If it's a velocity, then it's the velocity of point. So we have all discussed the vectors which are applied on particular point. So that is the ideal form of motion or statics, equilibrium. In real form, we all know that real objects are not like point masses. There is significant size. All real objects possess a significant size. They have significant dimensions. So we cannot treat real object as a point masses. As in Newton's law of motion, real objects have been assumed as a point mass just for modeling purpose. For modeling purpose, real objects have been assumed point masses, and study of forces and velocity and acceleration etc. have been carried out assuming real objects as point masses. So in reality, you will encounter objects with real dimensions, real sizes. So the study of real objects, their statics and their dynamics etc., it comes under a special branch of physics. A special branch of physics deals with real objects, which is called continuum mechanics. So first of all, rigid body. So rigid body means a body of finite dimension, any body of finite dimensions made of material, some material, and it is not deformable. Practically, there is no real body, real object which is completely ideal. Practically, all objects are deformable. But rigid body, as per its definition, it's a body where the different points, different small masses on this object will maintain the same distance under the force. Under different forces and motions, the distance between these particles, suppose these are points on this rigid body. So when this body will undergo some forces or it will move, then the distance between these particles, these points on this body will be unchanged. It will not change. all the particles points on the body will maintain a constant distance. That means this body is not deformable. Its size and shape will remain same under the application of forces. That is called rigid body. Rigid body means, simple term, the body is not deformable under the application of forces, and the distance between various points on the body will remain constant because body is not deformable body. So that is the definition of rigid body. Let it is a rigid body. Let there are 2 points A and B. So rigid body is defined as a body of continuous mass when different forces are acting on this body, then the distance between any 2 points on the body remains unchanged. That body doesn't deform at all. So that is called rigid body. We all know Newton had proposed laws of motion, but those laws of motion were for point masses. They were not for rigid body, for real objects. So these laws were modified. These laws were modified by Euler. The laws of motion proposed by Newton for point mass were modified by Euler so that they can be applied for real object or a system of different masses. A system of different masses m1, m2, m3, m4, m5, etc., which experiences an external force with the help of center of mass. In terms of center of mass, that we will discuss later, how Euler extended Newton's law of motion, which are called Euler's law of motion. Euler's law of motion, and those laws are given in terms of center of mass. So we know that Newton's law of motion, F is equal to m into a. This law is modeled for a point mass. Let this is a mass of point mass having mass m. If force is exerted F, then acceleration of this point mass will be F by m. This is Newton's second law of motion. This is applicable for a point mass. But in real life, we encounter with real objects having finite size. After Newton, few years later, Euler introduced the concept of continuum mechanics for rigid bodies, where he gave laws of motion which are analogous to Newton's law of motion, which have been derived from Newton's law of motion, but they are slightly modified so that they can be used for rigid bodies, real bodies, instead of point mass. So Euler's law of motion, first law of motion. So this is the rigid body. So Euler's first law of motion says that if force F is exerted on this rigid body, and this is the center of mass of this rigid body, and body having mass m, then Euler's first law of motion says that a center of mass, that is acceleration of center of mass of this rigid body, will be resultant force on the body. This is resultant force. If more than one forces are acting, then this is resultant force divided by mass of the body. This is Euler's first law of motion for rigid body, which has been derived from Newton's law of motion, second law of motion for point mass. This is for rigid body, real bodies. That is, acceleration of center of mass of a body will be equal to net force by mass of the body. So this is for single body. if there are more than one objects, let there are three objects, M1, M2, M3, and their center of mass is here. So let there is system of M1, M2, M3, and this is the center of mass. If force is applied F1 on M1, F2 on M2, and F3 on M3. Three forces are applied on this system. If we take M1, M2, M3 as a system, single system, then total three forces are acting on this system. So we will find F resultant, that is F1 plus F2 plus F3. Now by Euler's first law of motion, this center of mass will have acceleration. Acceleration of center of mass will be given by total resultant force divided by total mass M1 plus M2 plus M3. So this Euler's law of motion for a single body will be extended for a system having more than one masses in this form. That is, acceleration of center of mass is resultant force on the system. F resultant is F1 plus F2 plus F3. F resultant F1, F2, F3. That is the resultant of all external forces acting on the system divided by total mass of the system, M1 plus F2 plus M3. So this is the acceleration of center of mass of this system. So this is the Euler's first law of motion, which is applied for rigid body and a system of bodies having more than one masses. Now Euler's second law of motion. Euler's second law of motion is about the rotation. First law of motion, which is for linear motion. Second law is analogous to first law of motion, but it is for rotational motion. For a rigid body, if point A, about point A, net torque of different forces, that there are many forces F1, F2, etc. are acting. So the net torque of F1, F2, F3, etc. about A is T. Then T will be rate of change of angular momentum, that is dl by dt. L is the angular momentum of this body about point A, which is I into L. So net torque on this body will be equal to rate of change of angular momentum of the body about the point A. It can also be written as in terms of I into alpha, where alpha is angular acceleration. So that is the second law of Euler's law of motion, which is for rotational motion. So till now we have discussed Newton's law of motion for point mass and Euler's law of motion for rigid bodies. After discussing Euler's law of motion, we know that a force has two effects. First is linear effect for a rigid body, that is linear acceleration is net force by total mass. And second effect is rotational effect. This force will have torque and the total torque is equal to rate of change of angular momentum. This torque is created by the force. So a force has two effects on the real objects or real rigid bodies. So from Euler's law, we can say that a body is in equilibrium, perfect equilibrium, that is its linear motion and rotational motion should be zero. That is, motion means acceleration. The body should not have any linear acceleration and the body should not have any rotational acceleration. Then we say the body is in equilibrium. For equilibrium of a body, first condition is summation of total forces is zero. That is by first Euler's law of motion. That is, if summation of all forces acting on a body is 0, then net force will be 0, linear acceleration will be 0, body will not have any linear motion. That is the linear equilibrium, you can say. So you can say that is for linear equilibrium. That is the first condition of equilibrium. Second condition by Euler's law, second Euler's law says that the torque of all forces on the body should be 0 for its 0 acceleration. That means total torque should be 0. If total torque by all forces about a particular point is 0, then by this equation alpha will be 0. That means rotational acceleration will be 0. Hence, if a rigid body undergoes different type of forces and moments, and by first Euler's law of motion, summation of all forces is 0, then linear acceleration will be 0. Summation of all moments, torques about a point is 0, then its angular acceleration will be 0. So for equilibrium, that is linear equilibrium and rotational equilibrium. This condition is for linear equilibrium and this condition is for rotational equilibrium. So both these conditions should be met for a body to be in equilibrium. This is the mathematical interpretation of equilibrium, that is rotational and translational. Motion should be rotational and translational acceleration of body should be 0. Then body will be called in equilibrium. So this is Euler's first law of motion and this is Euler's second law of motion. Both are actually derived from Newton's law of motion. They are not called Euler's condition actually, because the basic law is Newton's law of motion. Still, for as a continuum mechanics branch, you can say this is Euler's first law of motion for rigid body to be in linear equilibrium, and this is Euler's second law of motion for body to be in rotational equilibrium.